Getting into this chapter 9 here. I've got the learning goals set up. I'm setting up my stopwatch. Okay, uh, let's do it. So I want to talk about the learning goals first because this chapter is massive and it's really important. So I want to make sure that we are focused on the goals, the learning goals. So in this lecture, this first lecture I'm going to give you on this subject, I think we're probably going to make it through the first 4 or 5 of these learning goals. So we're going to talk about the Rydberg equation and various regions of the hydrogen atom spectrum. Okay. Oh, don't do that. Undo. Okay, so we're going to talk about the hydrogen atom total energy operator. So we're going to build up the Hamiltonian total energy operator for the hydrogen atom. And then from there, we're going to go through the Schrodinger equation and all of these wave functions mentioned right here. So I'll loop back around to this at the end to see what we are able to cover. So very briefly, I'm just going to introduce this subject by saying this is what we're trying to get to. So we're going to use our operators, Schrodinger equation, and etc. And our goal is to try to come full circle and see if we can predict this spectrum. Okay. So, but now what we have here, this is the Rydberg equation, like was said on the slide. Okay. And hopefully you recognize this from Chem 109. Okay. So the difference in energy levels for a given value of n, right, principal quantum number n, can be calculated. And of course, here's the Rydberg constant in terms of wave numbers, but we could turn that Rydberg constant into joules or frequency, right, whatever we want, okay? And I'm not so concerned with you memorizing all of these various regions of the spectrum. Most notably, I think the Lyman series is a good series to kind of think about. So the Lyman series is for all you can see those are the really high energy lines. So that Lyman series is typically from n equals 2 to n equals 1. Okay, so that's kind of like our main, Lyman series. And then specifically Lyman alpha is given by this line right here at 125 nanometers. Okay. So then, of course, you can see we've got the Balmer, the Paschen, and the Brackett series. What you're most used to seeing with hydrogen is the Balmer series, okay? So that gives us those very famous red, yellow, and blue lines that you hopefully maybe you remember from Chem 109. But also, if you were to look at the sun with a prism, and don't do it directly, right? Make sure that you've got a prism and some kind of filter to keep you from looking at the full brunt of the solar spectrum, you would see those Balmer lines coming out of our sun, that red, orange, blue line, okay? So I'm going to move past this because our goal is to get to where we can predict this stuff, okay? So let's make our hydrogen atom operator, okay? So we first start with our physical picture in our XYZ coordinate system. And remember, we're going to give special treatment to that z-axis, okay? So we have our electron orbiting around a proton at radius r, okay? And this is showing you the particle on a ring model, but really this is a particle on a sphere model, right? So we know that we've got this angle phi in this plane right here, right? So my particle is spinning that way. But we also know that the particle is free to pitch, right, into those different angles given by ml, okay? So I'm also going to say we know that because this is really a particle on a sphere model, we can change the pitch of this rotation based on our values of ml, and that's going to be given by angle theta, okay? So when we put this energy operator together, we have the kinetic energy of the electron, we have the kinetic energy of the proton, and then we have the potential energy between the two. And the potential energy we're going to use is given by Coulomb's law. So this is the Coulomb potential that describes the attraction or repulsion of charged particles. Okay? So where we see this as a negative, that typically corresponds to an attraction. So a positive point charge being attracted to a negative point charge, okay? And so in this Coulomb's law, right, recall E, that's our fundamental charge. Z is the nuclear charge. So in the case of hydrogen, so for hydrogen, Z equals +1, right? There's only one proton in that nucleus, okay? And then we've got R, so that's the distance the electron is from the nucleus. And then we have the vacuum permittivity coefficient here, and then 4 pi, okay? So let's see here. So now when we look at this, okay, so I'm going to focus now down to this line. I'm replacing kinetic energy with our full three-dimensional spherical coordinate operator, which is negative h bar squared divided by 2 mass of electron. And then remember this del, right, del squared or nabla squared or the Laplacian, right? This gives us our r, theta, phi dependence, okay? Now, you notice here that we're talking about the coordinate system for the electron and the coordinate system for the proton, okay? We can actually marry those two things into just one single kinetic energy operator, okay? So this term here, so I've combined these two into just one term, because if we set our proton or our nucleus at the origin, right, 0, 0, 0, then our coordinate system, our del squared Laplacian operator, is just going to describe the electron-proton as one system, as one coordinate system. And also, we notice we've got mu, that's the reduced mass, so that's how I'm also able to combine those terms into one kinetic energy term, because I'm looking at the reduced mass. And so remember, that's going to be me times mp divided by me plus mp. And hopefully you remember, this is effectively just the mass of the electron. So even though I've got a mu right here for my electron-proton system, remember that's effectively just the mass of our electron, okay? So we've got our kinetic term and we've got our potential term, and we're ready to go. Beautiful. Let's keep it going. So here is the task at hand. You see I've got a big open white space and a bunch of nasty equations, so you know what we're about to do, okay? So there's a couple approximations that we're going to have to make in solving this system, and I'll point that out as we get to it, okay? So let's build this thing up. And so we're going to do the separation of variables, where I'm going to separate the radial components from the angular components, all right? And to make this easier, I'm just going to say psi equals r times y, so I don't have to keep writing those dependencies. But recognize capital R is the radial dependence, capital Y are the theta phi angular dependencies, okay? So let's build this thing up. So I'm going to first start by getting my Schrodinger equation put together. H psi equals E psi, okay? So let's do that. So I'm going to say negative h bar squared over 2 mu. And then now I'm going to replace the del squared with the actual Laplacian, okay? So let's get all of that stuff in there, plus 1 over r squared times the Legendrin squared. Okay, beautiful. And now that's times r y, because, right, h psi, right, we're calling psi ry, okay? And then now I can say minus the potential energy operator, which is going to be ze squared over 4 pi epsilon r little knot right there, okay? And that's also times ry. And then that all equals e to the, or e times ry, okay? So there's our full Schrodinger equation, okay? So as it turns out, we can look at this in an alternate form. So like I've got this full Laplacian right here. And there's a lot of kind of like shortcuts and steps I'm going to make that I'm not going to hold you responsible for. But as it turns out, you can make an approximation between these two terms to make this a little bit easier to solve. And that approximation of these two terms right here, the second derivative of r and 2 over r times ddr, that can be approximated as 1 over r times second derivative in r squared times r. I'm not going to hold you responsible for where that approximation comes from. We're going to take it, we're going to use it, and be happy that we have one less term to deal with. Okay? ry minus all this other stuff, ze squared over 4 pi epsilon times r times ry, all equals e to the ry. Okay, great. So now, as we start to inspect everything, and I'm going to distribute this through, because we're going to be able to start collecting constants and getting rid of terms that we don't need. All right? So what I'm going to now do in typical fashion, I'm going to push my constants here. I'm going to push them through over to the other side. Okay? And I'm also going to distribute all of these derivatives through to the wave function. So now I'm going to write that as 1 over r partial of r squared times r, and then distribute that through big R times y, okay? And then now that's plus 1 over r squared times the Legendrin squared times ry. And then now, because I multiplied through by negative 2 mu over h bar squared, this changes my sign right here. So that's going to become plus, and then I've got a 2ze squared, right, times mu, because, right, I'm distributing through those constants, over 4 pi epsilon r h bar squared. And now I'm going to take care of this 2 and 4 right here. I wanted to write those out just so you see where they come from. But let's just simplify those. Okay, so now that's just becoming a 2. Great. And then now, of course, that's still times ry. And now all of that equals negative 2 mu e over h bar squared times ry. And you can see this negative 2 mu e over h bar squared. That's our wave number solution, right? It's the same, the wave number k. Okay, so I'll write k with the little tilde, right? Because we know that that means wave number. Same k we've been dealing with, all right? Also, another cool side note, if we look at the collection of all of these constants here, I just want you to compare this for 1 second. I'm going to write our famous Bohr radius, which you all know is 52.9 picometers. So the Bohr radius equals 4 pi epsilon h bar squared divided by mu e squared. So let's just compare those for 1 hot second, right? You can see that even though I reduced that 2 over 4 to be 1 over 2, and there's a 4 right here, basically this collection of constants is where we get the Bohr radius from. So we're going to see this manifest just in the same way we saw our other equations manifest. Okay, and let's see here. I think I left myself a whole blank page. I did. Great. So continuing along. So I'll remind you from our spherical harmonics that the Legendrin squared times the YL/ML of theta phi. So all of that equals negative L times L plus 1 times YL/ML theta phi. So basically my Legendrin square operator, right? If you notice the way this is going, the Legendrin operator operates on the angular wave function, and I get back an eigenvalue and the original wave function. Okay, great. So we've already solved that. We did that in the other section. And I'll also remind you, right, when I look at like a term like this, let's say, so let's focus on this term, y has only dependent on theta and phi, whereas r is dependent only on r. So that means in this term, for example, my y term, I can take out in front because I don't have to worry about taking the derivative of y with respect to r because y is only dependent on theta and phi. And I'm going to do the same thing when I inspect through these other equations. So for example, right here, we can see r and y. We now know that Legendrin squared is only dependent on theta and phi. So also this big R right here, I'm going to be able to take that out in front as well. Okay. So when we do all of that, and I don't want to rewrite that big cumbersome equation, so I'm going to focus now on rewriting this big equation at the bottom and taking out all of those dependencies. So let's focus on this first term. Okay, that first term is going to become big Y, and so right, my big Y here equals my YL/ML of theta and phi. I'm just only writing Y to make it a little bit easier to write. Okay. So that becomes Y divided by R times the second derivative in R times R times R. All right. And now we can see already, if I go back and now focus on this term, 1 over R squared, Legendrin squared times R times Y. Well, I know I can take that R out. Okay. And when the Legendrin operates on Y, just as I showed you, we get negative L times L plus 1 and the original wave function Y. Okay. So now that second term becomes negative L times L plus 1 divided by R squared. And then I can substitute back that R. It doesn't matter what order it's in. And then times Y. Okay. And then now I've got my potential energy term that I'm going to write. Okay. And so now that's plus ZE squared mu divided by 2 pi epsilon R h bar squared, and that's still times RY, because this is just a bunch of constants, so there's no operation there. And then now that all equals my K solution, which I know K is negative 2me over h bar squared, right? M, remember, me and reduced mass, they're interchangeable for my electron-proton system. And that's still times Ry. Okay. So now what I can do, you notice that I've got a y in each of these terms, and there's no operations that I've got to carry out on y that would prevent me from canceling it out, right? I don't have any more derivatives or operations I have to do on y besides just multiplying, and that allows me to cancel it out. So I can reduce y from each one of those terms, okay? And I can't quite do the same thing for r because I have this pesky little derivative term, okay? So there's a little trick that standard quantum mechanics books do, and that is they make a new function u of r equal to r times r of r. And so I'll just remind you my nomenclature up here, right? Where I've written capital R, that's really my radial component of the wave function, okay? So this is standard manipulation in quantum mechanics. And the reason for that is because it makes our life a little bit easier, as we shall see. Okay, so I'm just studying my notes here so I can carefully transition those. All right, and oh, and then I did one last algebra that I forgot to do, and let's do that. So we eliminated y, and then because we've got this 1 over r here, we're going to multiply both sides of the equation by r. Okay, so when I do that, let's see here, what happens? Let's see. Oh, yes, when I do that, so I'm going to say multiply by r, and that cancels that r and that r. And then now I'm going to say multiply by r, and that's going to give me that r function. Also, because I'm multiplying everything through by r, I have to do that one as well. Okay, and then I have to do this one as well. And again, this is not something I'd expect you to just say, oh, multiply everything by r, and then come up with this new function u of r. This is standard manipulation because it's going to make the differential equations easier to solve. And so now when I rewrite this equation, let me just see what I have next. Yeah, okay. When I rewrite this equation now, I've got partial of r squared, and then r is my u of r function. Okay. And then now that's going to be minus L times L plus 1 over r squared times u of r. And remember, we have eliminated y. And now that's going to be plus z e squared mu over 2 pi epsilon r h bar squared. And once again, r times r gives me this new function u of r. And all of that equals negative 2 mu e over h bar squared times u of r. Okay, brilliant. So now I'm going to go to the next slide where I've got this equation written. And what I want to do is collect like terms. And I'm going to collect like terms for the kinetic energy and for the potential energy. Okay? So when I go to this next slide, it's the same equation here, but we've just rearranged it so that we can talk about this equation in a meaningful way. Okay? So here we go. So here is that. It's literally the exact same equation that I showed you before, but what we did was I multiplied this negative 2 mu e over h bar squared back through, okay, and collected like terms for the potential energy. And that's what the equation now looks like, okay? So we've got our negative h bar squared, 2 mu, second derivative in radius, and that's perfectly our kinetic energy operator. And now we get what's called an effective potential energy operator, which is this whole chunk in the parentheses, okay? And then, of course, that's times u of r, and then now all of that equals e times u of r. So what we've done here, we've eliminated the angular component, and really, I shouldn't even say that. We haven't eliminated the angular component. We've just reduced the angular component to its eigenvalue, which is that negative L times L plus 1, okay? So the angular wave function is not in here anymore, okay? Even so, I'll still remind you that my psi of r theta phi equals, let's see, that's going to equal, you know, the radial component times the YL ML theta phi component. And I know that my u of r just equals r times r of r. So I have a Schrodinger equation, right? This is my Schrodinger equation. There's my eigenvalue and my radial wave function that I need to solve for. And once I solve for that radial wave function, once I find a solution for u of r, then I can multiply it by r, right, to get, or excuse me, I would divide it by r, rather. And then once I get that solution, I plug it back in, and I'll have my total psi. So that's where we're going with this, okay? As it turns out, though, this Schrodinger equation can only be solved for various boundary condition cases, which is actually true of all of our Schrodinger equations. However, these solutions become a lot more condition specific. So there's three conditions we're going to look at. When L is equal to 0 or when L is non-equal to 0, when the electron is very close to the nucleus, or when the electron is very far from the nucleus, okay? And it's all about the angular momentum. And that's why we have these condition-specific cases, okay? So for example, I'll remind you that, so if we go to the next slide here, when L is equal to 0, the electron has no angular momentum. So let's not quite go into this yet. Let's just focus on that. So when L is equal to 0, there's no JZ component. There's no angular momentum on the z-axis, okay? And so now if we were to look at this effective potential energy, right, looking at these two terms right here, this is entirely, so here's the L equals 0, that's entirely what I'll call Coulombic. So in other words, we notice as the particle gets closer to the nucleus, right, as the radius decreases, the potential energy is really falling off. And I know it's going to negative values, but that's because when we developed that Coulomb's law in the first place, right, Coulomb's law is a negative potential when you have an attractive force, okay? So that's another condition that we're going to create is for all e's less than 0 for any bound state. So because of this Coulomb potential, right, because this Coulomb potential says the more attractive a force is, the more negative the potential gets, we have to also create this additional boundary condition that says for any bound state, the energy is less than 0 by definition, okay? So when L is not equal to 0, there is angular momentum on the z-axis, okay? And we'll see that there's competition now between the particle getting attracted to the nucleus and it getting flung away from the nucleus because it has angular momentum, right? So let's explore both of those in more detail, okay? So when L is equal to 0, and specifically when R is very close to the nucleus, so when this says R is almost 0, that means very close to the nucleus. So the electron has no angular momentum, and the force of the proton on the electron is purely Coulombic and attractive, okay? So that means that there's several chunks of this equation that we can eliminate, all right? So for one, why does it all equal 0? So I want you to compare this equation right here. We're going to compare this to the full equation that I showed you before, okay? Well, we know when L is equal to 0, right, this whole chunk goes away. So we don't have that to deal with anymore, all right? And now what we have left, and excuse me, also, why does this approximately equal 0? Well, it's approximately equal to 0 because we know that U of R equals R times R. And if this R is nearly equal to 0, then that makes the whole function nearly equal to 0. So that's where this whole side of the equation eliminates. Okay. And we don't eliminate it over here because, again, we're taking an operation on it. We're doing a derivative on it. Okay. And so now you notice what we have left when we go through that and pushing our constants through again, right? So then we get the ddr squared of u of r minus, and then now look at this, 2z over ar. So I collected all those constants for the Bohr radius, and there it is, okay? So now for this condition, our Schrodinger equation becomes very easy to solve. So this entire big nasty Schrodinger equation just reduces to this very simple form, and the approximate solution of this wave function is given by this polynomial. Okay? I'm not going to go through the ansatz method on this equation. We're just going to rely on this approximate solution for now. Okay? So it's a polynomial. So when L is equal to 0 and when R is very close, we can describe our wave function with this polynomial. Okay, let's look at a different condition. What about when L is not equal to 0 and still when R is very close to the nucleus? Okay, so what happens to our Schrodinger equation then? Well, once again, when R is very close to the nucleus, right, we eliminate that whole side of the equation because u of r will be a very, very small function, all right? But now also, the electron has orbital angular momentum, and it's being flung away from the proton, right? So if you think about that, right, imagine you're in the famous carnival ride or fair ride, where you sit and you lean up against that wall, and it starts spinning you around, and they drop the floor out, right? But you stay in position because your angular momentum is flinging you outward. It's flinging you like right up against that wall, and you're thrown back against the wall, and they can drop the floor out, and you won't fall down, okay? So this same thing is happening to the electron. The electron's whizzing around the proton at great speed, and thus it has a large enough angular momentum that attractive force is no longer important. So when r is equal to 0, its angular momentum is strong enough to dominate the attractive forces, and thus the electron is being repelled from the nucleus. And now specifically, the reason why we can ignore our Coulomb potential, right? So I'm going to cross that out because you can see in my approximate Schrodinger equation that Coulomb potential is no longer there. Well, this gets into what I like to think of as the quantized ice skater, right? So imagine you're spinning around and around, right? Your hands are spread out. What happens when you bring your center of mass closer in? You spin faster, right? You go much faster when you bring in that center of mass. The same thing is going on with this electron-proton system. The closer that electron is to the proton, the larger its angular momentum is, and the more it's getting flung out. So to me, this is the really cool age-old wisdom. If you ever have paused to ask the question, if the most likely place of finding the electron is near the nucleus, why isn't it right at the nucleus? And the reason for that is because it has angular momentum, okay? Because it's being attracted to the nucleus, but it's also being flung away from the nucleus at the same time, okay? So in this case, when r is very, very close, we can ignore the effective potential term. And when I push through all of my constants, I get this very simple Schrodinger equation to solve for the radial wave function. And the approximate solution is just simply a times r raised to the L power, where that's the same L quantum number. Okay, that's the quantum number L. Okay? And so again, like I said, all of these are approximate solutions, because what we're going to have to do is combine all of these into one solution eventually. All right? So let's look at the last condition. Oh, and sorry, the last thing I want to compare is, so the reason why, though, if you want to think about Coulomb's law and angular momentum being in competition, Coulomb, so the force, that's what that F is for, the force of Coulomb's law is proportional to 1 over r. However, the force of angular momentum is proportional to 1 over r squared. Right, there it is. There's the r squared, and there's the r. So for a very small r, when you take 1 over a very small number and then square it, that gives you a huge force due to angular momentum, much larger than the force due to Coulomb's law. Okay, so hopefully that makes good sense. Okay, so then finally, the last condition, when r approaches infinity. So both angular momentum and Coulomb's terms can be ignored because both forces become very weak when the electron is far from the nucleus. Okay? So the only thing that the electron has to consider is kinetic energy. Look, we got rid of all of these potential terms when the particle is very far away. And you can see here that this is a Schrodinger equation we've already solved, right? And you can see if I keep going through this on our standard ansatz method, right? So I add that over to the other side. That's going to be plus 2 mu e over h bar squared times u of r equals 0. We've solved this thing. This is literally just our one-dimensional particle in a box wave function, okay? And so now, as you're looking at this, you notice that there is this other condition here. This sign means assuming I can spell, it means asymptotically equal to. So there is an asymptote that this thing is approaching. And that asymptote is actually given by our boundary condition that E must be less than 0 for all bound states. And I've already showed you what that asymptote looks like. Here it is, right? As the electron is getting very, very far to the nucleus, or very far away from the nucleus, look, these two potential energy terms, they don't quite get to 0, but you can see that they're approaching 0. So when the electron is very far away from the electron, we're kind of in this region right here where we're approaching this asymptotic limit of E being 0. Okay? So we need E to be less than 0 for all bound states. And so what that means is when you're looking at this and you're going to set up the solution, okay, you're going to get something like K squared equals negative 2 mu E over h bar squared. And at first inspection, you might say, well, that's going to have imaginary solutions, but it's not. It's going to have real solutions because E already is negative. And so because that has a real solution, look, our term just becomes this simple E to the negative root of R. Okay? And the reason why we just have the negative term and not the positive root is because of that asymptotic limit. Okay? So I've been talking for 38 minutes, so it's time to cut it off. So this is where I'm going to end this. So we're going to put all of these approximate solutions together. So we've come up with 3 approximate solutions. 1, when the electron is very far away. 2, when the electron is very close, but it has angular momentum. 3, when the electron is very close, but it has no angular momentum. Okay? So when we put all 3 of those solutions together, we get something that looks like this. So we get this, and we're going to remember we've got U of R equals R times, let's see, what did I say? Oops. It's supposed to be R times R of R. So, and we're not gonna actually solve this thing ourselves. I'm kind of showing you the approximate way to solve this. Okay. So when we go to get back to our radial wave function R, we have this R raised to the L power, dominant when the electron is close to the nucleus. We have this decaying exponential in R, dominant when the electron is far from the nucleus. So that was the solution I just showed you. And then now we get this polynomial in R. That was our solution for when there's no angular momentum. And that bridges this kind of in-between region where there is angular momentum and potential energy that both affect the electron's position. Okay? And so some very smart folks have solved this problem and normalized it. And we're not going to do it ourselves, but I'm just going to present to you now the solution. Okay, so collecting our constants, we know that A naught is the collection of all of these constants. For convenience, this term rho is used to collect the 2zr over n a naught, where n has its usual meaning. That's quantum number n. Okay. And so now what we get, so you can see this r raised to the L power. That becomes rho raised to the L power because that approximate solution of r raised to the L power didn't contain all of those constants. Okay, and right, the Bohr radius is in that package. So there's a ton of constants here that are actually being raised to the L power. Okay, so this is that term right here. So this crazy thing, this L to the 2L plus 1 to the sub n plus 1 of rho, this is called the Laguerre polynomials. So this is the bridge that connects the solutions when r is very close or when the r is very far away. It also provides the connection for n and L. And I know that the notation of this looks fearsome, but it's really not. And when the Laguerre polynomials were developed, like I said, they actually provided the connection for n and L. And that connection becomes L takes on all values 0, 1, all the way to n minus 1. So these polynomials have standard notation based on that. Okay. So for example, when n is equal to 1, we know that L can only equal 0. And if I were to go and look up that Laguerre polynomial, then the notation of that polynomial would be, it would be written as L1n2, right? Because when L is 0, 2 times 0 plus 1 is 1, and when n is 1, L is 2. Or excuse me, that bottom term is 2, okay? So so in this notation, when we say L12, we know that we're dealing with n equals 1, L equals 0, okay? And then finally, we have this decaying exponential in r given to us by this term here. Okay, so that's about 42 minutes. It's kind of a long lecture. Apologies for that. So we're going to pick up right where we left off here. Okay, folks.